Yeah, you can start.
Okay,
Okay.
so good
So
afternoon,
good afternoon,
everyone.
everyone.
I earnestly hope that everyone here today and their family members are safe and doing fine in these tough times of the pandemic. And if there is anyone here who or whose family members are currently fighting the disease, I pray for their early recovery. Today, we are here for the first lecture of the Coherence Lecture Series. I welcome you all on behalf of Team Decoherence to today's talk. In this lecture series, we will hear from renowned physicists who are actively involved in research in particular areas of physics. So that everyone may get introduced to the various fields and ongoing researches in these fields. Today we have among us Professor Arindam Ghosh, who is a pioneer in the field of nanostructures and low-dimensional systems. Professor Arindam Ghosh is an experimental condensed matter physicist and a professor in the Department of Physics, Indian Institute of Science, Bangalore. He did his PhD at IISc and his postdoctoral research at University of Cambridge, UK. His areas of work are mainly in optoelectronics and nanoscale devices, and he has
And
done
he has done
groundbreaking research
groundbreaking
in these
research in
fields.
these fields.
He has several patents, including methods to enhance the sensitivity of a metallic piezoresistive transducer, vertical integration of nano and microparticle assemblies with atomically thin membranes and their applications and others. He is also the lead faculty member of the Quantum Materials and Devices.
It seems like we have a technical issue on part of the current speakers. So let's just give him a second to recover. Shamadeep, are you with us? Yeah, on call.
And Shanti Swarup Bhatnagar Award, just to name a few.
Of you.
He is also a
He is
fellow
also a
and
fellow
member of
and
several
member of.
societies and editorial board across the world. Again, just to name a few, he is a member of National Academy of Sciences, India, Indian Academy
Indian
of
Academy of
Sciences,
Sciences.
Indian National Science Academy, American Physical Society, and also member of editorial board of Nanotechnology and Nano Features, IOP, and Graphene Technology published by Springer.
there seems to be a little bit of technical issue there, but without further ado, I would like to invite Professor Arindam Ghosh to start his talk.
Okay, can you hear me?
Yes, sir, we can hear you.
All right, good. Yeah, I think this shows that we certainly need to improve our communication, maybe from classical to quantum as soon as possible. But let's hope that Shomadip will be back with us in a few seconds. Okay, good. First of all, thank you all, Shomadip, Nikita, and others who have made this possible. And this is a very interesting and important topic. I'm hoping that you can see my slide, and in case of any problems, I will time to time trying to understand whether you are listening to or you're getting the sound or not, because we never trust the communication link at these points. Okay, good. So I'm going to talk about quantum, and I know that many of you are probably either learning quantum or have learned quantum or are experts in quantum. So it's very difficult to summarize or to say everything which is digestible for everybody. So my goal will be to give you a flavor of what's lying ahead. And because these days the quantum is a buzzword and a very exciting word, and a lot of technologies, a lot of industry, a lot of governments are very excited by what's happening and what are possibilities really. And we should know at least a bird's eye view of what's lying ahead, why there is so much of excitement. Okay. Particularly because matter is quantum. At the end of the day, if you look at anything that is around us, whether it's a metal, it's a superconductor, insulator, whatever you see around us, after all, it's quantum mechanics that's holding the matter up. And we have been dealing with them since humankind started existing in that sense. So you can see there's nothing new about have been around the quantum concepts. And if matter is quantum, so are devices. If you take a look at the earliest transistor, which was made in 1947 by John Bardeen, who got Nobel Prize after that in 1956, if I'm not wrong, is exactly the same in terms of its physical properties or the way we can tune the electron flow. Electron is a quantum particle after all, and it obeys the laws of quantum mechanics. And the way we controlled electrons in 1947 is no different from the way we control electrons, which is going through an Intel Core i9 chip, which has got 1.2 trillion transistors in size of a fingernail, right? So, there is no difference in terms of what we have been seeing for decades. So the question is that why is so excitement about this new quantum? Okay, are we devising new quantum laws, or we are doing something completely different? So if I want to start with that, really, Richard Feynman, long time back, said that if you think you understand quantum mechanics, you do not understand quantum mechanics. And that is true. So one good thing about those who have not seen quantum mechanics so far, they do not need to feel left out, because even if those who are here with a lot of background with quantum mechanics still don't understand what it really is. Okay, right. So before going into what is new quantum, we'll have to know a little bit about what is old quantum and what's the foundational aspect of old quantum. But even before going there, I would like to flash a small slide about where we are today, and it didn't come within a day. It came over decades of theoretical and experimental breakthroughs in the quantum domain. It's very difficult to identify and pinpoint, these are the discoveries that actually have made quantum the way we are, but at least some overall, cornerstones can probably be defined. For example, certainly the day we came to know that energy is quantized probably is the first point. This is Planck's black body radiation, which required photons to come in bunches rather than as a pure wave, right? So that probably started in 1900. I mean, that's a long, long time ago. It's 120 years ago. Right? And then immediately after that, within 5 years, Einstein's photoelectric effect sort of came up and essentially said that, okay, electrons and can behave as particles as well. After that, 1923, this is the foundational aspects of quantum mechanics that was developing at that time. Extremely exciting era, about 100 years ago, when quantum mechanics and general relativity were coming up one by one, and eventually started collaborating with each other. But anyway, so then de Broglie came up and said that, okay, the wave and particles are, after all, the two different representations in quantum mechanics. In a couple of years, Schrödinger came, and that's what I'm going to show you in a slide. So Schrödinger came up and said that, okay, here is an equation which should tell you how quantum particle should behave. Okay, and this is how you can mathematically tailor, you can manipulate, and so on and so forth, a quantum particle. Okay, so that kind of a Newton's law in some sense for quantum mechanics. Okay, so that became a cornerstone of quantum mechanics, and after that, when quantum mechanics was formulated, of course, Einstein, and you all probably know, didn't really like it. And they were at loggerhead with the two different communities, Einstein on one side, Niels Bohr, Schrödinger on the other side, and the Schrödinger's cat thought experiment. And that's the reason I have put that one here, is because much of our current quantum technology is now based on these kind of thought experiments that was being carried out or being discussed, in 1930s, and very, very long time ago. So Schrödinger's cat thought experiment is essentially, if you do not see a cat which is inside a box, you do not know whether it's dead or alive, right? So that's the concept which Einstein was particularly against. And EPR paradox, the Einstein-Podolsky and Rosen paradox, came up, and they started saying that no, quantum mechanics is incomplete, and we need to have something like a hidden variable theory. And then eventually, there are a lot of discussions and debates and fights and conferences, etc. Eventually, Bell's theorem in 1960s. Look, it took about 30 years to resolve this, and Bell's theorem through Bell's inequalities and came up, and that kind of completely removed the hidden variable theory, and it was actually proven experimentally that after all, the foundational concept of quantum mechanics about this not knowing what is not measured became an experimental truth. Okay, so that's the very tricky bit, and that was got resolved. However, in between, the Bardeen, Cooper, and Schrieffer came up with this theory of superconductivity. The reason I put the superconductivity theory there is because today superconductors are the cornerstones or the platforms on which quantum computers are being built. And then, of course, the laser cooling started. We started, controlling atoms. And then 1997, Rydberg atoms, and we first demonstrated the CNOT gates, which is like a 2-qubit gating. And eventually in 2019, this last year, if you look at the quantum supremacy, was claimed by Google, showing that a particular quantum processor can outperform a classical process, supercomputers within reasonable time frame. Okay, so this is how the quantum discoveries, the quantum technology has really sort of progressed over the last 120 years. But let me tell you a very little bit, really one slide of introduction for those who have not seen quantum mechanics at all. The quantum mechanics really was, I would say, the start of it in the quantitative manner was by Schrodinger's equation, who said this simple equation, that is H psi is equal to H cross, that is Planck's constant, multiplied by d psi dt, which is the time differentiation of the state variable or the quantum state. So this H is the Hamiltonian, which represents the energy of the particle, and the psi is the quantum state. Okay. Now what happened is psi is the visualization of psi is it is nothing but an amplitude. Okay, like a wave has an amplitude, is like an amplitude, and hence in a wave description it is defined by some sort of a magnitude and a phase, which is time dependent or scale length dependent phase, right? Now what happened, if you look at the old quantum that technology, that means what we have been seeing for so long, I mean in materials around us, in devices around us, we have been able to what you call engineer the net magnitude of this quantum state, okay, the psi. That means if psi is taken as a probability of finding an electron, for example, a semiconductor or an insulator will be having 0 psi. That means there is no state, there is no probability of finding a particle which can conduct electricity. Whereas in a metal, for example, you can have psi to be finite, so that you can have states or electrons or any other quantum particle which can carry electricity. So most of our engineering, our understanding, or our development of material science have been over the last several decades based on this engineering of the net magnitude of psi. We really didn't go into the other concept which led to so much of fights between people like Einstein, Niels Bohr, and so on and so forth. Okay, so that's what you now going to change. So what we need to say now, okay, if you have psi, which is if there are states of a system which is not just one but multiple. For example, by state I mean to say, take for example the top, the rotating top. The top can rotate in counterclockwise or it can rotate clockwise, and these two are different states which do not mix with each other. Okay, you cannot mix a top which is rotating counterclockwise at the same time it cannot go clockwise, correct? So this is why these states are called eigenstates, which are mutually orthogonal to each other. Okay. Now each of these states will have its own energy. So that's more or less all I need to tell you about the foundational aspect of quantum mechanics that is needed. That means any quantum system can stay in multiple states. Okay, and these states can be orthogonal to each other. They do not necessarily mix. Okay, for example, a dead or a live cat cannot mix. It cannot be, if you see them, it cannot be simultaneously dead or alive. Okay, then we have, this is what the quantum technology is based on. So the basis of new quantum technology will be the superposition, and this is where the difference comes into play. If you have previously we have 0 and 1 as the two states of the qubit or a bit, for example. Now you have a new state, which is a quantum state, which can exist in 0 and 1 simultaneously, as long as you're not reading them, correct? So this is what you call a qubit. Okay. The advantage of that is that it kind of tells you that if you have a classical bit, which has got, say, for example, n classical bits, both of them can either stay in 0 or 1 state. So one up is 0, say, and the down is 1, whatever you choose. Then you can see that if there are n classical bits, each of them can stay in 2 states, then you have got totally 2 to the power of n configurations, or compositional or computational space. Now the difference, of course, in the quantum bit is that it's not only just 0 and 1, but the quantum state can exist in infinite number of combinations of this 0 and 1. Okay, as a result, n quantum bits or n qubits can actually simultaneously explode a very large phase space, and leading to exponential speed up in certain classes of problems. You have to be very careful. Everything cannot be done with a quantum computer much faster than a classical computer, But the basic concept here is because the quantum computer or a qubit can exist in linear superposition, that is alpha 0 plus beta 1, where beta and alpha are continuous variables. Since it can exist in much larger number of combinations, an n-qubit space is much larger than, it spans much larger Hilbert space than a classical computer. And as a result, it leads to a much faster execution of certain algorithms. And this is what created a problem. It turns out that some of the problems are where the quantum computer can be exponentially faster than the classical computer are search, which is through Glover algorithm, factorization, which is essentially factoring two prime numbers, for example, simulations, optimizations. There are several other possibilities. Now, this factorization has created a problem because this can lead to de-encryption of some of the passwords that we have used. RSA protocol is one of the encryption protocols which are used in lots of secret documents, whether it is in bank account, yours and my bank account, transactions, online transactions that we do, that disclose very strong secrets of nations, documents, they are often encrypted, among others, the RSA protocol, which essentially is a product of two very large prime integers. Now, what people are scared is that if quantum computer becomes a reality, then those encryptions becomes de-encrypted in a much quicker time than what people were hoping for when they encrypted those data. Okay, and that is why the governments, the banks, and so forth, all other people are scared and they want to have a quantum computer. So that's great. Okay, but we can use the quantum computer for many other purposes, and I'm going to give you some ideas later. Okay. Then how to build a quantum computer, and the building of quantum computers have been discussed by many people, but originally when it came first, David DiVincenzo at IBM at that time said that, okay, so set 5 ground rules, okay, to build a good quantum computer. First, you have to have qubits. The qubits themselves must be well characterized, and the system should be scalable so as to include large number of qubits. Great. And I'm going to show you in a few minutes what those good qubits are. People initially say that, okay, and they still say that the electron spins are very good qubit. The spins can be up or down. So this is like qubit of 0 and 1. And you can actually, this is a quantum variable already, so it can exist in linear superposition of these two states as long as till you measure. Okay, so there are a large number of different possible realizations of qubits that have been suggested. You also have a second law. Then it must be possible to initialize the state of each qubit into a simple fiducial state. You must be able to create your qubit at the beginning. Okay, you have to initialize it in another way. Okay. For example, you need to be able to create in 0 state or 1 state when you start your operation. Then we have the quantum state of each qubit should be long-lived enough. That means long decoherence times, and this is where you come into play. You already have given your name of decoherence, so you should be short enough. Okay, sorry, you should be long enough. You should live for a long time. The decoherence times should be as long as possible, and the lifetime should be at least long enough to do a number of gate operations, which is obviously correct. That means the qubit should not lose the quantum information that it has. For example, you see the qubit is a quantum superposition of 2 states, alpha 0 plus beta 1. So this condition should remain for sufficiently long time so that you can apply certain gates, okay, and perform the logic operations with quantum algorithm, not with classical, but with certain algorithms can be applied. Okay. Yeah, there is. So number 4 is there should be the universal set of quantum gates available that can be used to build unitary transformation corresponding to any arbitrary algorithm. It's not going through the detail of it, just it means that we should be able to change, or we should be able to change the quantum state by using an external mean, which is called quantum gates, by applying some pulse microwaves or whatever is the gating procedure. We should be able to enforce certain unitary transformations so that we can do computation. So that's the algorithm which should be implemented. And finally, once you have done the algorithm, you should be able to read it out. Okay, like every qubit, like the way you have a classical computer, what is the state of a classical bit is usually saved in capacitors, in memories, etc. You should also be able to do the same for a quantum bit, which means it should be possible to address or read each qubit individually and to measure the quantum state of each qubit independent of the state of others. So by measuring one qubit state, you should not change the qubit state of the other. Then in that case, your reading will not be proper. Okay, so these are the 4 guiding principles that led to a lot of activities over the last 20 years or so to build the quantum computer. And today in 2019, we have a computer which is which is claimed, although it is not beyond it's not beyond controversy, and IBM doesn't accept Google's claim. Google claimed in 20th September 2019 that they have achieved what you call quantum supremacy. What is quantum supremacy in quantum computing? Quantum supremacy is the goal of demonstrating that a programmable quantum device can solve a problem that no classical computer can solve in any feasible amount of time. Okay, so if you see, Google had made this quantum computer or a processor called Sycamore quantum processor, which is 53 qubit processor. And well, it was 54 and one of the qubit didn't work apparently. 53 qubit quantum processor, which solved a task in 200 seconds. And this task was specifically designed, and that detail I will not go into, in 200 seconds that they claimed would take a supercomputer 10,000 years to solve. Okay, so and that essentially made them claim that the quantum supremacy has been achieved and the era of quantum computers have begun, and so on and so forth. Okay, so they used superconducting qubits in which the state of a Josephson junction, which if you don't worry, if you don't know, that's a different question, to use the superconducting qubits. And as I said in the beginning, that qubits can be from many systems as long as they obey the DiVincenzo criteria that I showed earlier. That means they should be long-lived enough. They should the decoherence time should be small. Okay, there should be 2 states. So the whole idea is that you should be able to create 2 separate states, which are 2 separate quantum states that can be superimposed with each other. And there are several possibilities. For example, superconducting qubit, semiconductors using various kinds of realizations, for example, quantum dots and so on and so forth, are another big contender of eventually making a quantum computer. Trapped ions are very important in this. Photons, light, okay, because photons are quantum particles too. And then defects and color centers. There are several such entities or platforms on which a quantum computer can be built. Okay, now as I said, the interesting part is not just quantum computation, but the basis for new quantum technology. There are several. I just gave you the superposition and how superposition has taken to quantum computer. But what's the next basis of that makes our new quantum technology? The next is measurement. You see, the measurement is, if you see, a quantum state is not a well-defined system till you see it. That means the moment you try to see, it collapses into one of the constituent states that it was composed of. So for example, Schrodinger's cat experiment is one of the well-known one. As long as the cat is inside, you do not know whether it's dead or alive. Only the moment you open the box to see it, you either find the cat to be dead or you find the cat to alive. That means the system collapses to one of the eigenstates. is most interesting, and that's actually the spooky action at a distance called entanglement. You see, these are different aspects of quantum concept that were not explicitly being used in old quantum computation, engineering, but that's what is being happening now. So the entanglement, probably some of you have already seen this. I'll just repeat that. If you create a quantum state of entangled state of two particles, which each of the particles can exist in two possible states, which is the qubit, for example. And if so, take this balls as qubits, and the up and down states are red and blue, for example. Okay, so then you have a quantum physicist who entangles them, and now what happens is that once you entangle them and you put them in boxes, and what's the state of them in the boxes, and then the two boxes are sent to very far off distances, and arbitrarily far off distances. And then if one of them opens and sees the state is blue or the state is down, whatever it is, and then the other one will have to be red or the other state. Okay, so this is what quantum entanglement is. And this is what Einstein didn't like at all. Einstein said that means you essentially have the information that what's in the other ball will be instantaneously. Okay. So it turns out that that's not really a problem, and there was no information that was being exchanged physically, and that's why there was no problem. But in any case, Einstein hated quantum mechanics before that, and he said that if quantum theory is correct, it signifies the end of physics as a science. But that's fortunately didn't come out to be true, because today we have quantum communication essentially based and on this particular concept. Okay, this technology of sharing information, which is entangled, is called this quantum key distribution, is one of the major application area. The basic idea is simple. You create a pair of entangled photons, and this photon goes, one of the photons is kept at the origin, which is Alice, or one of them, and then the other photon essentially is transmitted. And then you arbitrarily, flip the you keep on creating these entangled photons and leave one with you, and the other one can be sent to the other party, right? Now, what interesting part is that if someone wants to hack it, then they have to see what is the state, for example, and the moment they see the state, they will have to change it, because that's what quantum mechanics has said, that the moment you measure the state, you collapse it to an eigenstate, okay? And hence what happens, the sequence that you were sending, the correlation is lost, and you can immediately say that someone is listening or someone is trying to hack. Okay, and this is the basic concept of the secure quantum communication or quantum key distribution. Okay, and now there are already strong emphasis of how to get this, how to implement this. Do this through fiber optic cable, and you start with a single photon source, and then you have on the other end single photon detectors, and in between you can have this fiber optic cable through which photons can travel. Okay. By the way, I hope I am still there. If any of you are listening, can you please say yes?
Yes, sir, you're very much audible. Good,
excellent. All right. The next is, of course, quantum communication. In the quantum communication, you don't need in free space, you do not need the fiber optic cable, but you can do essentially by sending directly through free air or vacuum. Okay, and this has been done quite a while ago. In 2014, this happened in La Palma and Tenerife, where next to Spanish coast, with two small islands, and quantum communication was demonstrated. And recently, China managed to do this from Beijing to Shanghai over 1,200 kilometers. They sent the quantum long distance quantum communication link. After that, of course, they have also been able to communicate between China and Austria through satellite. And this is something which is happening in India as well. Okay, so what's the horizon for what we see in this quantum communication horizon? First, next goal, of course, will be this quantum key distribution over metropolitan cities. So we would like to have different parts of the city connected in quantum network. Okay. And then we would like to see the distance to be going up, so 500 kilometers, or now this long distance quantum communication becomes more and more difficult because the photon intensity goes down, because fiber optic cables, they absorb photons very easily. So it becomes difficult to make them very long. And we would like to see new technologies coming up through what is called quantum memories, quantum repeaters. And getting long distance quantum communication becomes technology. Hopefully that will happen in some time. This also will require developing new technologies. I'm going to come to this part later again, so you don't need to worry too much. And eventually, what we are going to see is probably multi-city network, and then quantum entangle-based network, and then we are also going to see eventually what you call cloud computing and quantum internet. That's a long-term goal, really, at the end of the day. So that's quantum communication. And the last one in this basis of new technology that I was talking about is topology. I'm not going to talk about in detail of this at all, except for the fact that topology was actually one of in its formative days. It's essentially about the property of geometric phases of the wave function. As I told you, a wave description, the quantums have both amplitude and a phase. And this phase, which now called is Berry-Pancharatnam phase, had a contribution from Pancharatnam, who was in Bangalore, by the way, in the mid-90s. Okay. And this topology gives us a completely new class of systems, material devices, where the electrons can avoid disorder and hence zero resistance states and so on and so forth. But anyway, we'll talk about that on some other day. So if I summarize what I have told so far, that quantum technology that we are looking at ahead of us is based on three major directions: quantum computation, quantum communication, and third is quantum sensing and metrology. Wait for a second on that. But I must also add that in addition to that, there's a huge amount of theoretical aspects that there is post-quantum software, quantum algorithm development, and post-quantum cryptography. What is post-quantum cryptography? You see, people have realized that, okay, our cryptography, that RSA protocols and so on and so forth, are no longer safe if the quantum computer really comes up at some point of time. So we now need to create cryptographic advances or advanced in cryptography or encryption of secure or of sensitive data, which will not be possible even for a quantum computer to hack through. Okay, so this field of cryptography is called post-quantum cryptography, and there's a huge amount of work that is being done at various levels in IISc, in various departments globally, to create these post-quantum cryptographic protocols, which will be safe against quantum computer-based hacking. Okay, so if I summarize the first two, for example, the quantum themes, you see, what are we expecting in a quantum computer? Okay, a quantum computer is, the computer will give us speeding up quantum advantage in certain amount of protocols, certain functions, for example, factoring, simulations. We expect that some of the major social life directions will get strongly influenced. For example, drug discoveries, finding new chemicals, because you can span, you can look at the space of very quickly in much faster times. Search, write ingredients, so that drug discovery can be hugely affected, hugely benefited. Then you have got traffic optimization, because so many degrees of freedom, particularly in India, it is obviously Bangalore. You need to find optimal routes and network optimization. These are immediately foreseeable good things that a quantum computer can give us. Okay. If I look at the quantum communication, you can see the cryptography is one thing that we are looking at very carefully. We are looking at secured key quantum transfer. That will lead to some form of long-term data security, which cannot be immediately hackable by eavesdroppers. Then we have secured online transactions, paying money, and eventually, probably at some day, it will be quantum internet that we'll be talking through. Okay. Okay. The third one, which probably is the reason I kept it for the last, is because this is probably the first that will come to us when it comes to social life. Okay, and our social structure. And quantum sensing and metrology. For example, clocks. Synchronizing clocks to extremely accurate timescales. This is important for GPS. When we do navigation through Google Maps, our positions are determined by exchanging information or signals from the satellites. And for this thing to work very well, we need to create extremely high accuracy time. So this is what atomic clocks are. I'll come to that in a little bit later. We have medical diagnostics, imaging, and imaging in a completely different way that will be possible. I'll give you some example in a minute. Imaging below the ground through looking at the gravitational constant imaging, for example, navigation. So these are areas which might be affected by sensing and metrology. So, but I didn't talk about what sensing and metrology is. So let me explain a little bit about what is sensing and quantum sensitivity. Why is quantum sensitivity so interesting, given the foundational concepts that we have developed so far? So we know that the new quantum properties that we are seeing are quantum superposition, quantum measurements, quantum entanglement, and quantum topology, of which first three are more important as far as this talk is concerned. So what does it do to sensitivity? Why sensitivity is affected? Okay, suppose I have an apple. Okay, I'll give you an example through this measurement of distance. Suppose I have an apple, and for some reason, whatever it is, I want to measure the diameter of the apple. Okay. Now I have a scale. I use a scale and I measure the diameter. Okay, that's great. But scales are not the same. Different scales are different, and they will give us different numbers, right? So I take another scale, and then that scale gives me another number L2, for example. I take another scale and get number L3, and other scale get 4, and so on and so forth. Okay, so every scale gives me a particular number. And we know that if there are n different numbers, the mean value of the diameter of that apple is given by 1 over n, sum over all else, correct? All the readings that I have got so far. Now each scale here is a system, and you are using a system to measure the diameter, okay, get a reading out of it. Now if I get this mean, there is also an error. Right, and we know, for those who have seen statistics, the error, when I say classical, is when these scales are completely independent of each other, classical entities. This error will always go as square root, which is a standard deviation, of 1 over n multiplied by Li minus average L whole square, right? As a result, if you have n scales, then the error will go as 1 over root n. It turns out that if you manage to entangle your systems, the scales, suppose, are quantum mechanical particles, and quantum mechanically and they are entangled with each other, then in that case it can be shown, and this is what is called Heisenberg's limit. This error is no longer going as 1 over root n, but it goes as 1 over n. Now, it's slightly difficult for me to tell you why this happens, simply because there is an unitary transformation that takes place, but there is now sufficiently strong theoretical foundation to believe and to show that if you, instead of using independent measurements, if you make your measurements entangled, that is, your measurement systems entangled, then your error in the measurement goes as 1 over n. And that means something really interesting. It means that in comparison to a classical measurement, the quantum measurements goes as 1 over root n. So if you use, instead of 4 scales, if you use 1,000,000 scales, then our error in the measurement of the diameter of the apple is 1,000th of what is the minimum possible error in classical measurements. And the minimum possible error in the classical measurement is called standard quantum limit. And this new error, which is because of the entangled scales, is called a Heisenberg limited sensing. Okay, and this can create havoc. This can create so many applications is beyond our imagination, or just imagination is the only limiting factor, to be honest. For example, what can it give us? A photonic sensor, for example, a multi-photon interferometry. You can use quantum imaging with squeeze states. Squeeze states are nothing but, suppose you have got photons, approximately, say, of a light. The light is a wave, and a wave will have phase and amplitude. And then what you do is that and both are fluctuating quantities, okay? Because if you want to know phase very well, you cannot know amplitude very well, and vice versa. So squeeze states, essentially you squeeze your error in one of these variables at the expense of the other. So you can use these photonic sensors to measure displacements, and this is being used in LIGO, for example, in gravitational wave detection, where you really need to measure displacements in the order of 10 to the minus 19 meters, really small. Okay, and similar kind of interferometry, multi-photon interferometry with squeeze states, one of the huge applications of photonic sensing. You can use these atomic sensors now using atomic condensates, okay, cold atoms. A collection of atoms at extremely low temperature is also a fantastic sensor, because what happens is that cold atoms are entangled, right? And atoms have mass, so they are affected by gravity. Okay, so by using quantum entangled atoms, okay, at very low temperature, you can measure the value of acceleration due to gravity, for example, to an extremely high accuracy, up to pico-g, or over 1 meter distance. And what is the advantage of that? You can look at oil and gas resource, for example. If you are looking at natural resources which is embedded underground, then you can take these atomic sensors and scan it and see the variation in the atom in the g, or in the acceleration due to gravity. If there is oil reserve somewhere, then you should be able to, or something else for that matter, you will be able to find it. Or if there is seismic changes, for example, earthquake prediction and so on and so forth, tsunami, volcano activities. So these are completely new directions which require measuring these parameters very accurately, the value of gravitational constant and things like that. So they become possible, okay, which are completely impossible in the classical sensing ideas that we have, technology that we have today. Quantum imaging is a fantastic example. Okay, entangled light beam and quantum radar, ghost imaging. For example, ghost imaging is that if you have something which is in front of you, a block in the classical path of light, then how do you image that? What is behind it? Okay, and in principle, that's possible if you use entanglement. I'll give you an example with quantum radar, for example. A quantum radar is nothing but a imaging which you can detect a small tiny element which is reflecting light in the presence of a large, highly illuminated background. Okay, for example, an aeroplane which is a stealth aircraft, for example, which you cannot detect. You think it's it's invisible to standard radar. But what you do here is that instead of standard unentangled imaging process, which is on the left of the slide that you see here, where you transmit a signal, it gets reflected by and comes back to the receiver. Instead, what you do, you use entangled photons. So very similar in some sense to quantum communication ideas. You create a signal and also create an idler photon, which is transmitted directly from the transmitter to the receiver. Now, the other part of the entangled photon, which goes to the object that you want to see, and then gets reflected and reaches the receiver. It should, in principle, then be correlated. And it has been shown that ideally, it should be possible to detect objects which are illuminated by a large noise background or illumination. Okay, so that's the idea of quantum radar. And similarly, there are other applications of spin qubit in high resolution magnetometry. This is where measuring magnetic fields down to few femtotesla or few attotesla is possible, which is roughly the kind of magnetic fields that's there in our electromagnetic activities in the brain. So it has been an electric field as well. So it has been used or suggested it will be used in brain imaging and so on and so forth in years to come. Good. So I am giving you more or less ideas of everything here. But the question is, very good. So when are all these things going to happen? So one has to have a realistic idea how the quantum technology community and so many people are working on this particular field and expecting these things to realize or materialize. Okay, so I'm going to give you some sort of idea about what you call a quantum timeline. Okay, when are we going to expect these things? First is, quantum computation. The quantum computation will involve annealers. I've explained it, so I'll leave it for the time being. The noisy intermediate scale quantum processors, the Google's 53-qubit processor, which now has been shown to or claimed to have the quantum supremacy, is an example of noisy intermediate scale quantum processor. Okay, so for now to about next decade or so, it's more or less certain that we will be in this state. We will continuously be increasing the number of qubits. In fact, the number of qubits are increasing faster at this stage than the Moore's law, which says that every 2 years the number of transistors doubled in a processor. But right now the number of processors are doubling faster actually. But these are not corrected for decoherence and other errors. So these are very noisy intermediate scale quantum processors. They do not have too many usefulness, but maybe we will find it soon. But if you look at the fault tolerant gate-based quantum computers, which does something really useful in quantum domain, both either what we know about or maybe something we learn in the future, that's not going to come in the next 15 years or so. I mean, that's roughly the timeline which the community is projecting. If you look at communication, the quantum key distribution is already being done. That means sending the quantum entangled photons and receiving signals and analyzing them and making this quantum communication secure. That is already happening. But whether the networking is not particularly there yet, and hopefully by mid-2025, 26, 27, probably intracity and intercity communications networks will come in. And then probably somewhere around 2035 onwards, we will probably be looking at quantum internet. Okay, we do not know cloud-based quantum computing, with so on and so forth. Okay. But if you look at the sensing and metrology, there are higher number of goals that can in principle be available in relatively shorter span of time, say 10 years or so. And I have given some examples. You can see atomic clocks. Atomic clocks are essentially the timekeepers. Okay, they give you time very accurately. As I told you, the atomic clocks they are based on the certain rubidium, cesium, some atoms which emit very precise, electromagnetic signal when they relax from an excited state. And you measure the frequency of that signal, and they're very accurate, and they can give you accuracy of time to 15, 16 decades, one part in 15, 16 decades. Okay, and that is the kind of accuracy in time that is required to navigation, and probably in about 7-8 years time we will probably don't need a GPS system for navigation anymore. And that's very interesting and important, because then you don't, that's from the point of view of security, that will be quite important. Okay? So GPS free navigation, because of very high time accuracy timekeeping, is going to be one direction. The gravimeters and gradiometers, that means measurement of seismic constant, the acceleration due to gravity and seismic activities and so on and so forth, using atomic condensates and other techniques, probably are going to happen over the next 5-6 years, and by 2025 we will hopefully be moving towards something of that sort. The magnetometers for brain imaging, cell imaging, and so on and so forth are probably going to be in the similar time scale. Within about next 10 years or so, we should be having it. The quantum LIDAR. LIDAR is a light intensity detector and range. So that's all these quantum imaging, quantum radar, ghost imaging, and so those fall under this category. They probably are going to come in as well. So what do we do? I mean, as a community, why is it so difficult? I'll give you a little bit of a flavor of why is it so difficult, and why is the technology needs to develop. Okay, so I'll give you an example, what you call a close-up of a technology. Okay, sorry. Okay. So take a look at optics. In my laboratory here and several other people, we are strongly involved in optics of some form. So I'll tell you, if you take this whole range of quantum technologies that we mentioned today, the computation, communication, sensing, for example, many of these elements that are required in this are optical elements. For example, single entangled photon sources. You need sources of entangled photons if you want to use communication. If you want to make photonic qubits for computation, if you want to send quantum key distribution, you need them. You need for sensing and metrology, for example, imaging, quantum radars, and so on and so forth. You need these single photon and entangled photon sources. You need the similar single photon detectors as well from the other side, right? You have to measure them. You need optical fibers, you need integrated photonic waveguides, you need modulators, you need transducers, you need converters, you need memories and repeaters. Some of these technologies are at an advanced stage, some of the technologies are not even there. For example, the memories and the repeaters are not even there today. We do not have a well-defined quantum memory. I mean, these are absolutely cutting-edge global research. How to create a memory in which you store the information, quantum information, for some time to be read out later. Okay, so this is a completely even unknown. But there are suggestions, there are platforms that have been suggested, and experiments are coming very, very recently. Okay, just to give you how hard it is, I'll take this first example of one of those components, or single photon source. Okay. Now you need to satisfy a very stringent criteria for these single photon sources. For example, you need to have fidelity 1. That means it will be highly entangled. I mean, for entangled applications that require that. Okay. Efficiency should be 1. That means for every time you need one entangled photon pair out, you should be able to have it. So that's one efficiency, completely deterministic. You need to have the right spectral range. So they need to be their communication wavelength of 1550 nanometer. You need to have them very close to that spectral range. You need to have very bright sources, because there need to be a lot of photons coming out every second in the orders of tens of megahertz. You need to also have sources where the multi-photon emission is 0. It's called purity. That means I want just 2 photons. I don't want more than 2 photons. Okay. For every emission, there should be just 2 photons. That means the multi-photon emission should be 0. They should be able to operate at room temperature, and they should be indistinguishable photons for all purposes. Now, it turns out that these are not easy. Okay. So getting all these in the same system is extremely difficult. And as a result, several platforms have been suggested. We have spontaneous down conversion from nonlinear crystals, which when light comes and hits these nonlinear crystals and then goes out in 2 photons, which are half the energy, and that's conserves both the energy and momentum. So there's a huge amount of material research that is going on in that direction. We have got 4-wave mixing. We have got atoms and ions as sources. We have quantum dots. Quantum dot sources are very interesting because this is something which, multi-photon excitation. You can excite an electron to higher energy and then let it relax in 2 states, and then it's essentially gives you very high quality multiple photons, entangled photons, okay, through quantum dots, and nitrogen vacancy center. So you see, in order to get these few criteria, it is almost like Divine sensor criteria for one single, photon source. So each and every requirement of quantum technology will require a huge amount of research and development to achieve this stringent criteria, okay? And this is where research comes into play, okay? Good, I'm done. What I will do is I'm going to give you one last slide where I essentially listed what is different about the quantum technologies, okay? In comparison to the technologies that have been going on, we have seen since the Renaissance, since industrial revolutions, the way technology has developed. What's different about quantum tech? First thing is that science is still evolving. Means that we have to understand how materials behave in order to be applicable to quantum applications. For example, even we still don't know whether the superconducting qubits will be the final winner, right? Because there are so many others, and there are concerns, there are technological bottlenecks that need to be sorted. And as a result, research and technology development must go hand in hand. They must feed back into each other to get to the final product. The second is, again, the quantum technology has already identified a very well-defined goals. We need to have a quantum computer with this criteria. We need to have quantum simulation, quantum communication with these parameters. We are looking at 1,000 kilometer or more quantum information transfer, for which we need these elements. So it has got a very well-defined global goals, which is somewhat different from other technologies. For example, nanotechnology, where the goals were relatively open-ended. We would like to shrink the system and look at their properties, and if properties becomes interesting, we will apply them. So it's slightly less open-ended. Quantum technology is less open-ended than nanotechnology. So, that's a little different. It needs, we need to have very strong classical technology. I mean, we need to have making devices, softwares, material synthesis. We will have to have the other technologies that have been developed. The quantum technology will have to build on them rather than come from completely new direction, okay? And its immediate strategic importance. You see, the quantum domain, the kind of application that I told you so far, it's from radar, from submarine detection, cryptography, the long-time data security, and so on and so forth. These will have to be developed in different nations are developing independently. There are very little, there are so much of strategic concerns involved that these need to be developed independently by every country at certain level. And it will be very difficult to buy. Tomorrow, I don't know whether it will be easy to buy a quantum laptop, so who knows, okay? Industry is also learning, and so, industry is learning what kind of systems are good businesses and so on and so forth. So there's a lot of new things about it. This is a transient stage, so to speak. Okay, this is my last slide. The promise of quantum technology, that this is a very well known statement of Richard Feynman, in some sense, starting from the quantum computer, because we would like to, at the end of the day, these are all very interesting science, right? Because you are looking at a quantum world, and the best way to look at a quantum world is with quantum technology. All right, good, thank you. I think that's all I had to say. If there are questions, then I'll be happy to answer.
Yes, so we have received several questions.
All right.
Yeah, I'll ask Rishik to read it.
Shall I stop sharing, or I think let me stop sharing and then we can, or maybe,
Yeah, sure.
all right, tell me. I don't know. Yeah.
Okay, so
No, tell me your
firstly, I
name.
apologize. So
Tell me your name first because I can't. Ah, okay. Yeah, go on. Shomuddin. Yeah, okay.
It seems Shamideep has a problem. Rishik, could you continue?
Yes. There is a question asking, while performing the measurement of state of a qubit using some probe, will the state of the qubit be disturbed?
Yeah, exactly. So that's exactly the problem, or that's exactly the foundational premises of quantum mechanics. That if you do not know the state of the qubit, you measure it. But when you measure it, it collapses to one of its eigenstates, or one of. So what happens? Any state of the qubit is a quantum superposition of n number of states. Our qubit has got two states, but a quantum state will be, there will be n number of different states. But when you measure it, you disturb that, and it will be then seen in one of those n states that it is composed of. Yes, it will be disturbed.
Yes. Pawan Dubal is asking about universality in quantum computers. We know that NAND and NOR gates for classical computers are universal. So tell about the universality in quantum computers.
Okay, so there are universal set of gates that have been defined. There are single qubit gates, there are 2-qubit gates. There are various algorithms in which you apply gate. The gates are essentially unitary transformations in the state of a qubit. Now, the and nor so the classical concepts of gates are somewhat modified in case of quantum computer. There are people who are working on quantum algorithms. They will be tell you much better. But for example, the Hadamard gate, the CNOT gates, these are gates which are 2-qubit gates, and the single qubit gates are also being applied. You need to have little bit more in this direction. To once you know what unitary transformations or gating what quantum gates are, it will be easy to understand what are these unitary transformations.
Yeah. So Pawan Dubal is asking one more question. What is the range of switching frequency at which quantum computers operate?
Right. I mean, see I do not know what switching frequency is in this case. I mean, usually there are microwaves which are involved, and that's primarily because the switching of one state in a qubit, particularly those which are based on superconducting qubits, the two states are separated by few milli-electron volts, and the milli-electron volts are essentially in the gigahertz to tens of gigahertz region, and so you use these microwave to switch the states of the qubits. So, but I think it's slightly different from the switching frequency that you mean. But this is what how you apply or manipulate the qubit states in a quantum.
How different is quantum communication with photons for QKD different from optical communication?
Okay, so the optical communication is well, everything is optical communication. At the end of the day, if you use photons, you are communicating with optics, right? So I don't think optical communication is a differentiating factor. What is differentiating is quantum communication and classical communication. In classical communication, you essentially fire photons. Well, there is no entanglement between the photons. Okay, not that all quantum key distribution require entangled photons. There are, that's not the point here. But in classical communication, the polarization, the quantum properties are simply not used. But everything is optical. The basic platform is not different between the basic communication platform is not different. It's the mechanism and the information that is being transferred will have a classical and a quantum component.
Could you please explain about the decoherence lifetime in qubits? How can we make this long-lived?
Very good question. So look, I mean, this is an open problem, and qubits have developed over the years, and orders of magnitude increase in qubit lifetimes have happened, and it's still increasing in most of the qubit platforms. Now, it depends upon what type of qubit you're talking about. Say, I will give you an example of a semiconducting qubit using say silicon. There, the typical decoherence time will be in the orders of milliseconds. Okay, whereas if you take again in semiconductors, there's a charge-based qubit, there's spin-based qubits. The spin-based qubits will have a slightly lower decoherence time, whereas the charge-based probably has a slightly higher, about 2 milliseconds or something of that sort, if I remember properly. Now, the decoherence is what? Decoherence means how, if you take a simplistic view here, how a quantum system interacts with its surroundings. Okay. For example, electromagnetic fluctuations around a qubit will lead to additional transitions of the qubit state from 1 to 0 or 0 to 1. Okay, so the interactions of the electromagnetic environment with your quantum system will determine how prone your quantum system is to decoherence. Now, this is a very interesting point for another reason. You see, if you want to make the system longer, the decoherence time longer and longer, by appropriate shielding of the qubits from the environment through electromagnetic shielding, that's a heavy amount of electromagnetic shielding is required. Decoherence times becomes longer. Okay, there is no doubt. Appropriate material platform is also very important. Okay, for example, in silicon. You see, there's a silicon which has got a silicon isotope of 29, and there's a silicon isotope of 28. Now, silicon isotope of 29 has got nuclear spin. Now, what happens is that if you're trying to make a qubit platform with silicon 28, this existence of 29 can actually create a problem. So there is a whole concept of enriched silicon platform for long-lived qubits. That's important. So there are many ways of reducing the decoherence and increasing the decoherence time. That's completely dependent on individual qubit platform. However, you also have to understand that you cannot make it completely isolated from the environment, because in order to apply your gates, for example, the universal gates, you need to have some form of interaction from the environment in order to initialize, in order to read, and so on and so forth. So at the end of the day, you have to have a compromise.
Does the conventional complexity classes like P and P have corresponding analogs in quantum domain?
Analog, you mean to say p-n junctions?
No, P and P complexity classes.
I don't know this.
Okay.
So to go to the next question.
Is it possible to make a quantum artificial intelligence in near future?
Yes, that's a very good question as well. So there is a lot of thought about it. So obviously, at the end of the day, the big goal, the big picture is how to create a quantum neuromorphic design, okay, in which the it's a qubit which will store the information as well as process it. Okay, right now a brain-inspired or a neuromorphic artificial intelligence device essentially is one in which you store and process at the same time. You don't use one-to-one architecture where the storage and processing are done in two different blocks. Okay, so obviously there are now suggestions that okay, can we create qubits where you can do the processing and storage at the same time. So it will eventually become a neuron and a bit and a qubit all coming together and making a quantum neuromorphic system. That will probably be the ultimate in computing.
Is it necessary to always make use of superconductors to transfer data to or from a quantum computer, or are there any alternatives to it?
Okay. No, of course it is not. It's a very good question. Superconductors are right now being used in realizing a qubit. Okay, the Josephson junctions in a superconductor is a platform, one of the qubit platforms. Now there are plenty of qubit platforms which has got nothing to do with superconductivity. For example, semiconductors do not need superconducting platforms. Okay. And ions, the NV centers, there are defect centers, the color centers in diamond, for example. These are all completely non-superconducting platforms of quantum computation. Now, regarding the transfer that you're talking about, there are, although superconductors can transfer electrical signals very quickly, very nicely, I mean, it depends upon how you transfer from one qubit information to the other. Or outside, how do you read it, right? And there you don't need superconductivity. It is usually done through electromagnetic sensing, electromagnetic pulses, and readouts, which are high frequency electrical signals. So no, I think so far as quantum computation is done, the primary technology is in making a qubit.
Why are the quantum computers so huge? How are they powered?
Right. Okay. So the pictures that you see is, of course, Google ones, and in which, okay. So right now, you see the superconducting qubits have got certain structures. It's got a cavity, okay, in which the pulses, the gigahertz pulses, get coupled to the superconducting Josephson junctions, which is kept inside. Okay. Which is essentially it's a box which is defined, whose size is defined based to make sure to resonate with certain modes. Okay, and because gigahertz frequencies are usually long wavelengths, the corresponding structures are also larger. So each cavity takes significant amount of space. But now if you make 50 of them or more or whatever it is, then naturally you need a much larger amount of space, which you need to cool down simultaneously to below the superconducting critical point to have the quantum structure. So to answer your question, it is because of the cavity resonator, which couples the microwave to the superconducting qubit, is itself large because of the design concerns that makes superconductors very large, or the quantum computers processors very large. Yeah.
There's a question about, is India investing in development of quantum computer?
Yes, there are. There's a significant development, and in various ways. Particularly in superconductor TIFR, in IISc, we have got Professor Bihor Singh, Professor Baladitya Suri, who are looking into superconducting processors. So yes, of course, there is a significant amount of development, a significant amount of research that has started in India, I would say. Yeah.
What kind of gates are meant to be used for quantum computation, and at what time scales do they work?
Right. So, I mean, what types of gate is difficult for me to understand, tell you without going into the architecture of a superconductor, of a qubit structure and the processor design. there could be okay. Usually, in a nutshell, and I'm not an expert for this, it's essentially what you do is that you take a Josephson junction of a superconductor, usually made from aluminum, and then you shunt it with resistance and capacitors and create what you call a transmon qubit. And these transmons are communicated with microwave channels, lines, which will essentially which are used for gating some readouts and so on and so forth. So a processor essentially is that. That means a bunch of RF lines, which let me see if I can show you here. No, actually, it will take a little time. So yeah, so it's through RF, the radio frequency RF lines, that you apply you communicate with individual qubit transmons. All right, what was the second part of the question?
At what time scales do they work?
All right. I mean, look, at the end of the day, you have to work within the decoherence time, right? So it depends upon which kind of system you're talking about, and it's typically a few milliseconds for gate operations. Okay.
Will it ever be possible for a quantum measuring device to be portable?
Good. Right. See, hopefully, yes, it should be at some point possible to have portable quantum devices. I'm just trying to think whether there is already any portable quantum device. If you quantum random number generators usually come from mobile phones in some of the ways, so in that sense, probably it is already portable. But that's a different one. But no, at this point of time, I cannot think of. But in few years, probably yes, whether it's a clock or whether it is a magnetometer or things like that, will probably be possible.
There are quite a few questions. Will you be taking those?
I'll take them till 6:30.
Yeah, sure.
Okay.
Arijit is asking, are quantum computers Markovian? If not, then can some memory effects reduce the level of security quantum computers have?
I don't think I'm eligible to answer this question. I mean, I don't know whether it is there is a question of that sort at all. I mean, the quantum computers are, if you can look at it, it's nothing but a collection of qubits, which are, two qubits are entangled to have a gate operation, and you read out the state of the qubits after the operation is over. So I'm not entirely sure what the security concern is here. So I can't really answer that question.
How exactly are the photons used in quantum communication entangled, and how is the information extracted out of such entangled pairs?
Okay, so that's what I told you. So you create two entangled photons in several different possible ways, and which I showed you at the last slide of mine. And for example, if you show the if you use this nonlinear crystal and you use this parametric down conversion, you create two photons from a single photon of half the energy, two photons of half the energy. And then you use single photon detectors on the other side. And when these single photon detectors should be sensitive to individual collection of individual photons. And then what you do is that you measure the entangled how entangled the two photons are by using two detectors and correlating them. Okay, that's called correlator. So so that's how you detect entanglement. So any form of communication, which is whether it's for imaging or for quantum information transfer, you look at the correlation between the photons, which is emitted, and the one which is the two photons, which is with the sender and with the receiver. Yeah.
What are the applications of quantum mechanics in organic electronics?
Okay. Right. So organic electronics per se is after all, it uses molecules, right? And it's molecular states which then couple to leads and then form this electronic path, and you can modulate that by making different electronic components. Now, every molecule at the end of the day is quantum mechanical itself. Okay. As a result, its performance is always dominated by quantum mechanics. It has to be. Whether it is quantum, the kind of quantum behavior that we discussed today, where four main features of quantum, which is superposition, measurements, entanglement, topology, etc., whether those are explicitly used, that will depend upon the design of the organic molecule, okay, or organic electronic structure. So if one can tomorrow make a molecule which can exist in two quantum states that can be tuned with an RF or some other electromagnetic means, then in principle you can make a qubit from organic molecules. There's nothing that's stopping us, okay? And use its electronic properties to read out or to manipulate the quantum state. But there is no explicit application of the quantum technological aspect that we talked about today. I think that is connected to quantum molecular or organic electronics.
There are a couple of general questions.
Mm-hmm.
If someone has to be involved with quantum technologies, should he or she be studying engineering or physics?
Well, I mean, one good thing about quantum technology is that it doesn't care whether you're a physicist or an engineer. I mean, it's important, of course, to have a background for quantum technology, for quantum mechanics. I mean, many people have asked me in the past about, okay, what's the right background? You need to know quantum mechanics. Without knowing quantum mechanics, of course, you do not know. You need to have the foundational concepts like what measurements, starting from Heisenberg uncertainty principle, Schrödinger's equation, to found other kind of aspects. For example, how to the measurements, the Bell states, what are maximally entangled states, and so on and so forth. So these are concepts that is needed. Now, whether your core discipline is in engineering and you understand these aspects by taking additional courses is not a problem. I mean, then also it's possible. Or you can take these courses as your core discipline, like in physics is your core, then you will naturally learn these. But then you can take engineering aspects as your to apply or to make certain application in quantum domain. Both are possible, both directions are possible, but you need to have a way at some point of time in your curriculum, you need to have strong quantum background or create a strong quantum background or these foundational aspects of quantum background. So for this, you need to know a mathematical You need to have this the necessary mathematical background as well as and the quantum mechanical aspects. So if you have these two together, then what your core discipline is shouldn't be a big problem.
Thank you very much, Professor. Now I'll pass it on to Nikita for a vote of thanks.
All right.
Firstly, I would like to apologize on behalf of Team for the delays that happened as well as the network issues we faced. And I would like to thank Professor Arindam Ghosh for taking time out of his precious busy schedule to talk to us and answer so many questions. It was a thoroughly enlightening and fascinating talk on applications of quantum technology and where the field stands to go. We would also like to thank the Dean of the UG program in IISc, Professor Anil Kumar, for making this talk possible. We would also like to thank Team Pravega as a whole for supporting us and enabling us to conduct this talk. Lastly, we would like to thank the audience for attending this talk. We really hope you enjoyed it. We have more talks and workshops planned for you, including Professor Jyotsna Komaragiri's talk tomorrow at 4:30 p.m. on searching for the fundamental building blocks of the universe at the Large Hadron Collider as part of the Coherence Lecture Series. Please visit our website to know more. And again, I would like to thank Professor Arindam Ghosh again for doing this. Thank you.
Thank you. Bye.
Yeah, I'm terminating the call.